Okay, so the formulas, the propositions we've been proving so far were kind of childish, right? So A implies B and so on. So that's, you know, there are no connectives except for implications. You have no ands, no ors, so conjunctions, disjunctions, no quantifiers. So now I'm going to show how to reason about more complicated formulas that do contain these logical symbols. And the trick is to use so-called introduction and elimination rules, which are simply lemmas. And the nice thing about lemmas is you can treat them just like functions or terms. You can use check on them to see them. And you see, true.intro, the introduction rule for true, is simply the formula true. I should say this thing about introduction elimination rule comes from natural deduction. This is something you probably have seen in some previous course. For example, at the FU, I guess logic and modeling would have had them, and maybe even the course before, logic and sets, but at least logic and modeling must have had those rules. So true is very easy. You can always introduce true. You can always, if you want true, you have it, and it's called true.intro. Not here says, if you want to prove not of something, you see where this question mark M1 means something, some meta variable, then you need to provide the following. You need to prove that if you assume M1, then you can derive false. So this is how, in some sense, not is defined, at least in one direction. So if you want to prove not, it suffices to, you know, to assume whatever and then to derive false. So that's a proof by contradiction, or at least a proof of negation is called. Then there's and, which is if you want to prove A and B, you have to provide A and you have to provide B. I'm giving it better names. I don't want to pronounce question mark M1 and so on, right? Or is like this. So you have or left and or right. So here you can, right? You can say that for all B, if you can prove A, then you can prove A or B, regardless of the value of B, right? As long as you have A, you have A or B. And for right, it's the other way around. And for some technical reason, the display is quite different, but it's really the same spirit. We won't notice a difference when we use these rules. So basically here, if you have B, then you also have A or B, right? For all AB, right? I mean, here what happened is that one of the for alls got transformed into some meta variable. I mean, this could have been for all A and then A and then A and B, but for some reason, Lean decided to transform it into this kind of thing, but it really behaves almost the same, okay? Then you have if and only if, right? So A if and only if B. If you want to prove that, then you have to prove that one implies the other, and then the other implies the one. And for exists, whoa, that looks nasty the way it's written, because of a technical representation of exists. So exists are represented under the hood in terms of a lambda, and we don't see that very clearly here. So I think I'm going to skip exists for now. We're going to see it in action. But basically, what I can say without explaining the details is to prove that there exists an X that satisfies, you know, a certain property M2. It suffices to prove that property M2 for some, you know, some witness W, right? So for any W, for all W, if you manage to prove the property, then you prove also the exists that goes with it. But something is a bit wrong with the display here. You know, what I really would like to say here, and that would be accurate, is exists an X such that M2 X. In fact, I think it's so correct that I can probably put it in here, and Lean will not come. Well, okay. Oh yeah, it doesn't like the M1s. Okay, it does something. I said nothing. But you see, this is the spirit of the rule. If you prove it for W, then you prove it for some X. Okay, whoops. And then the elimination rules, they work the other way. So you have your, there's no rule for false, I should say. There's no way to introduce false. Which is good because you don't want to introduce false. On the other hand, you can eliminate false. So if you've managed to prove false, so elimination goes the other way. It means you have an assumption of a symbol and a connective, and you want to extract some information from it. So if you have proof false, then you're in a very lucky situation where you can prove anything, including M1. If you've proved M1 or A and B, then you can extract A, or you can extract B. So these are two separate rules. The OR elim is quite complicated. So you say it's kind of a little logical trick. You have an OR, A or B. And then you say, well, if you can prove under assumption A that you have C, and under assumption B that you have C, then you can prove C for any C. So this allows you to do a case split, right? So your goal is foo, and you have you know that you're either in case A or B, then you can do a case split, and then you prove under assumption A, you prove foo, and under assumption B, you prove foo. We're going to see it in action. It feels quite natural when we apply these rules to actual problems, right? I mean, this is quite abstract nonsense now. It will become concrete nonsense in an instance, and maybe it will even make sense. So then elim, you see you have if and only if, right? So if you have an if and only if, you can extract one implication, or you extract the other implication. And then finally, exists. Oh yeah, that's another one that's complicated. It has a bit the same flavor as the OR, and this should not be so surprising because an exists is like a gigantic OR, right? So if I say there exists an X such that P of X, what I'm saying is basically P of 0 or P of 1 or P of 2 or P of 3. I don't know which one, but there exists one. So it's just a big OR. And for that reason, that rule has a bit the same flavor. But I'm not going to explain it in detail. Again, it's easier to just use these rules. First, there are no symbols for implications, and there's no symbols for all. And the reason is that these are really baked very deeply into Lean. So the concept of implication and the concept of for all are so intrinsic to Lean that you don't even need lemmas to do with it. So all you need is, well, intro and apply. The two tactics. They are specialized to work basically with exactly those symbols, right? Which is why they worked earlier, right? You remember we had for alls. We wanted to move the for all variables into the context. The first thing we did was intro, right? So that was intro was basically if for all introduction, but we just called it intro. So that's what's going on here. And you see there's no true.elim because that would be trivial. I mean, there's nothing to extract from true. If you know true, you know nothing, right? Whereas if you know false, then you know everything, okay? And then you have some symbols that are just defined. So for example, print, not is defined like this, right? Could have defined it ourselves. It simply implies false, right? So not foo is foo implies false. Right, it takes one argument here, right, the foo, and then it returns foo, false. This is an if and only if that we're going to use later. So it's called not def. It's kind of the definition. And then there are two more lemmas that are quite useful because we reason in classical logic in Lean. So Lean has a kind of intuitionistic build-up for those who know what that means. But on top of that, you have classical axioms. So Lean is always classical, even though it feels a bit intuitionistic. Again, if you don't know what I'm talking about, just ignore that segment. So yeah, so included middle EM says that for any proposition, either you have P or not P, right? And you also have the principle of proof by contradiction. So you want to prove here M1, well, you assume the negation and you prove false. And this is quite similar to what we saw with the not here, not intro. But here you had a not, and you had none here. So that's a proof of negation. So earlier I should never have called it a proof by contradiction. And this, which has no not here and no not here, is strictly speaking for logicians a proof by contradictions. Although mathematicians, I think, call both, proof by contradiction. Because they are classical anyway, it doesn't make a big difference to them if there's a negation or not, or if there are 5 or if there are 7. Okay? And now we prove our first proof or lemma that talks, about and about conjunction. We're just going to show that it's commutative, right? So, well, actually, I'm going to remove the proof and do it live. That's going to be more instructive, right? So how we do this is we try to make sure that Lean kind of parses what we do, right? We don't want an error 10 lines later because we haven't put our and. So we put the and here. Okay, now we get an error because there's an empty, well, it doesn't finish the proof. Well, we can even put a sorry at the end, so then it really shuts up. And we look at the goal. And again, there's a strategy to it, and the strategy is given in the Hitchhiker's Guide, but the idea is very similar to, the strategy we saw in the first lecture, which is here we look, there's an implication on top. So that means we're going to use an intro. And I'm going to call it HAB because it's the formula looks like A and a B. So often you give names to your hypotheses and lemmas that resemble the shape of the formula. You don't want them to be too long, like H, A, and B. That's usually overkill in a short proof. But I mean, this is your choice. I'm not going to subtract points because you use longer names, obviously. But try to choose meaningful names, not X, Y, Z, A, B, right? It has to be some system. Okay, so okay, we have A and B. We need to prove B and A. There are several things we could do. We could look at HAB and try to see what can we extract from that. That would be an elimination rule. But at this point, we're not so equipped with dealing with that, actually. What's better is to focus on the goal for the moment. Try to bring the goal. You see, we have into a nicer form. We have a conjunction at the top level. We need to prove two things. Well, the natural thing to do is to say, okay, let's prove one of them first, then we'll prove the other ones, because the two are completely independent, right? Of course, they have the same hypothesis, but we can prove them in sequence. So what does that mean? We want to prove something, where the goal is a conjunction. That means we use the introduction rule for conjunction. And here you must notice the naming is possibly counterintuitive, because as far as we're concerned, what we're doing is we're breaking the conjunction apart, right? We're not introducing it, it's already there, and we're breaking it apart. So why do we call this even intro? Well, the reason is because we're doing backward proofs, and the names were chosen by people who were working forwards. So to them, this was an introduction rule, right? If you go backwards, then intro means tearing things apart, and it's as simple as that. Okay. So you'll get used to it. I mean, at some point your brain gets washed, I guess, and it becomes all natural. So we apply the introduction rule for conjunction, for and we end up with two goals, just as I promised. One where we have to prove B, and the other one we have to prove A. Okay. Then what can we do? Well, we have this, you see A and B as hypothesis, and we want to prove B. That looks very much like an and elim right. You see, A and B implies B. That's what we have, right? So we say apply and elim right. If I put the comma, right, then I see exactly what it wants from me. Right. Let's see. So when you use these rules, the best is to, I mean, here you see it pops 3 goals, and that is too much, right? And the reason why that happened is because I should really have specified, you know, which has some hypothesis I want to work on. If we don't, then lean, you know, it even wants to prove that there exists a prop or whatever. This is a very strange looking goal, right? If we end up in a situation like this, then that means probably we're not working optimally. Unfortunately, lots of things in lean are accepted, you know, by the system, even though they don't intuitively make sense. So here, you know, what I really want to do is take this hypothesis HAB and say, this is what I want to eliminate on, right? And then that worked. I think with the other approach, it would have worked as well. You see, because the first, the goal works by assumption here. You see this assumption with A and B will match the one with the question mark. Well, I can just say assumption, right? And then I'm left with the other goal. So that would have worked as well. But my recommendation is just, you can pass it as argument in some sense, right? So elim right accept as first, you see, well, let's see, as first non-implicit argument accepts a conjunction, a proof of conjunction. So this is what we pass here. And then we do the same again, apply and elim right. No, this time it's going to be elim left. HAB, right? Because we want elim right, we want to extract the A, not the B. Write a comma, it's happy, goals accomplished. And at this point, I can remove the sorry, and I can remove the extra comma. This is one way to write this proof, right? And here's, and these applies could have been exact indeed, right? So I could have written exact. That's just aesthetics. And here's another proof of the same thing, except that we also need to introduce a few things at the beginning, right? But this time we use curly braces. So you see here, when I'm here, I see 2 goals. And if I enter a curly brace, right, then I zoom into 1 goal. I see only 1 goal at the bottom, and I see only 1 goal here. So when I read the proof script afterwards, I see what happened there, right? I see that after this command, I ended up with 2 goals. This is the first one, this is the other one. And I can see the whole tree, you know, of goals and sub-goals if I use these curly braces systematically. So I recommend using them, but they're not mandatory. But they help remove some clutter from the proof state. Right? Here's another example with an OR. So this time I'm not redoing it from scratch. I'm just showing it. So first we do some introduction again. Then we have HAB here. We have B or A here. So now we have the choice, you know, well, we have a priori the choice. Should we work on the hypothesis? Should we use elim on this or intro on that? And actually it's premature to use intro on the conclusion, because when we use an intro on an OR, we have to choose if we go left or if we go right. But at this point, we don't know yet where we're going to have to go, right? So in this situation, it's better to work on the hypothesis. This is too much information. It's better to work on the hypothesis here to, you know, what we want to do is break it into 2 cases, the case where A is true and the case where B is true. And then based on which case we're in, we're going to use a different branch to prove the conclusion. So this is exactly what this proof script here achieves. So first we use the OR elim rule, and we pass HAB, right, to avoid this strange looking goal and so on. So it's good practice with elims. Then we have 2 goals. You see here you have A implies plus. We do an intro. You don't need the S when you just do 1. So I'll just remove it, but it doesn't matter. Okay, so far so good. And then, well, now we have the A, which is really good because we need to prove B or A. And we have A. So we're going to use an intro write. And this is what it looks like. So I could also write it in several lines, I think. Right? So here, if I write it in several lines, first I apply intro write, and then I can say assumption. So that would be the easiest way to write it. Here I've used a slightly more macho idiom, which is to pass the hypothesis directly. And because of the way that the type looks like, you see it takes a mandatory argument of type prop called A first. So that one I say I don't want to specify it, so I just pass underscore. I think it's just A. No, it's not A, sorry. And then maybe it's B. Yeah, it's B, you see, but I don't want to know. That's too much information. So I put an underscore. I don't want to specify that. Whoops, it's gone. It's gone. It's there. The B I don't need to specify. And here it takes, it takes the, here it's called B. For us, it's called A, right? So the A's and the B's are reversed, which is a bit confusing. And you see the other case is completely analogous, but it's symmetric with left instead of right. So more examples, modus ponens. I'm not going to show all of them, but you see it's more intros, more applies. Right, so modus ponens is just that if you have A and B and you have A, then you have B, right? So it's just an apply and then an exact or an assumption. Not is more interesting because first you do an intro and then you have not. And then what you can do is a not intro, right? And then that gets rid of one not. Okay. At this point, what are we doing here? Intro, all right. So here we have an implication. So we do an intro to move that part to the hypothesis. And at this point we have A and not A. And we want to prove false, right? So we have A and not A, we want to prove false. That should definitely be false, but how do we do it in Lean? Well, the trick is to remember that not A is defined as A implies false. And that Lean works up to definitions and computation rules. So we can, in most contexts, just pretend that not A is A implies false. And we want to prove false. So this hypothesis is going to help us because it has false in its conclusion. So we can just apply it, right? And then once we've done that, well, we just have to prove A, which is one of our assumptions. So, and then if I put the comma, then we see that we're done. Right, so this little end game here is very cute, but we must remember that not A is the same as A implies false, and it's very easy to forget and to be stuck in the proof just because of that. So here, more proofs of the same flavor. You can play with them at home. You can erase them and try to refine them if you have the time. Here you have an example of an exist. So when you want to prove an exist, the trick is to provide a witness. And the idea is a bit as with conjunction, disjunction, sorry, an or, right? With an or, you wait until you know enough, whether you want to go left or right before you make the choice. And here's the same thing. You advance in the proof to the point where you know which witness is going to work. And until then, you don't instantiate. But here it's a very easy proof, right? Which number, find a number whose double is itself. Well, 0 will do the trick, right? So we just apply the intro rule with the witness 0. And then we have to prove that double 0 is 0, and REFL is able to do that. So this section here of the course is very important. This is really the bread and butter of proofs. This will pop up over and over again. You will have, of course, connectives, quantifiers, over and over again. You'll have to apply intro, with the intro rules, the elimination rules, and so on. So if you don't fully understand what happens now, don't worry too much, in the sense that it will come back and you'll have more and more opportunities always to get a good grip on it. But at the same time, this is really fundamental to the course.